Hello students, we discuss today the force constant of a bond, that is, which one is represented by small k, force constant. The force constant of a bond is a measure of strength of the bond, that is, stronger the bond, higher will be the value of that force constant, while weaker will be bond, smaller the value of that force constant. That force constant represent magnitude of force, that is how much force is required to compress or stretch bond, compress or stretch, for stretching or for compress that bond during vibration, how much force required, that one is given by, represented by that force constant. If bond is stronger, that required more force for vibration. Therefore, for stronger bonds, value of K is also maximum. And for weaker bonds, for vibrations, force required is smaller, therefore value of K is also small. That value of force constant, that means depends on strength of bond, and strength of bond depends on the atoms between which that bond exists. That the magnitude of that force constant depends on chemical nature of atoms. That chemical nature, that magnitude of force constant, that is strength of bond, which is directly proportional to magnitude of force constant. Therefore, we also call that force constant as a strength of bond, that both are directly proportional. Therefore, that strength of bond, that is force constant, depends on chemical nature of two atoms between which that bond exists, and therefore that depends on chemical nature only. Therefore, isotopic molecules, where atoms are different mass numbers but chemical nature is same, therefore for isotopic molecules, values of force constant are similar. That value of force constant can be calculated for any bond using their fundamental frequency of vibration. What is fundamental frequency? That molecule when placed in zero vibrational level, that frequency during that in that level, the frequency of vibration is known as fundamental frequency. And there is relation between K, mu and fundamental frequency is Phi0, that is fundamental frequency is equal to 1 upon 2 pi into under root K into mu. That mu is reduced mass, K is force constant. By solving this, we got equation, that very important equation. Write this as K, that is force constant, is equal to 4 pi square into C square into Phi 0 bar square into mu. Consider that, for simplicity, consider that square terms together. That is, k is equal to 4 pi square c square v0 bar square into mu, that is reduced mass. How much terms? See how many terms are there? 1, 2, 3, 4 terms. This one is very important equation for problem solving purpose. That is, if you consider that, see here, one problem is already given. The fundamental frequency of vibration for HCl molecule is 288,560 meter inverse. That one is given in meter inverse. Calculate the force constant of the bond. In that equation, all terms are constant, and that new reduced mass we calculate in for that given molecule, that in HCl, that atomic masses are known, and from that we calculate that reduced mass value. Pi is constant, that v0 bar is here, bar is not given, but there must bar. v0 bar is a fundamental frequency and c is constant. Therefore, when molecule is known, reduced mass is also there, we can calculate, and from fundamental frequency we calculate value of k by solving. Practice that. There are some more problems are given here by using scientific calculator. We use, all of you solve that. Then mode of vibrations are and condition of IR spectroscopy, that is vibrational spectroscopy. We already discussed during first part of this topic that molecule possess different mode of vibrations. Depending on symmetry of that molecule, there are two equations are given for calculation of number of modes of vibrations. For calculation of number of modes of vibration, if molecule is linear, then equation is number of modes of vibration 3n minus 5 here. That n given is nothing but number of atoms present in that molecule. Number of atoms present in that molecule. For non-linear molecule like water, NH3, that number of mode of vibrations are 3n minus 6. Remember these two equations. For linear molecules, 3n minus 5. For non-linear molecules, 3n minus 6. Then if we consider IR spectrum of carbon dioxide and water molecules. In previous exam, many times this question asked on this point, that is discuss the explain the vibrational spectrum or IR spectrum of carbon dioxide and NH3, ammonia, or sometime asked water molecule. That is, carbon dioxide is linear or non-linear? It is linear molecule. Therefore, first calculate that number of modes of vibrations by using 3n minus 5. Number of atoms 3. Therefore, 9 minus 5, 4 modes. How many modes of vibrations? 4 modes. Which are that? Stretching and bending. 2 stretching modes, 2 bending mode. 2 stretching modes, symmetric stretching and asymmetric stretching. And 2 bending modes, in plane bending and out of plane bending. If you consider four modes, then there must be four lines in a four signals in a IR spectrum of CO2. It is expected, but actually CO2 IR spectrum of CO2 shows only three signals that indicate out of these four stretching modes, one of the mode is IR inactive. Then which mode and why that mode is IR inactive? We already discussed at the first part of this topic that what is condition for IR spectrum, which molecules are IR active and which are inactive. That is, those molecules which possess change in dipole moment or positive dipole moment, that molecules are only IR active and that are only studied by using IR spectroscopy. While other molecules whose dipole moment is zero, or those molecules which do not possess change in dipole moment during the vibrations. See here, two things are there. Those molecules whose dipole moment is zero, and another, those molecules which do not shows change in dipole moment during the vibrations, that molecules are IR inactive. Therefore, molecules like H2, Cl2, Br2, whose dipole moment is zero, that are not studied, that cannot be studied under this IR spectroscopy. Then if you consider these four modes and their dipole moment, then it is observed that the symmetric stretching mode shown in diagram, where dipole moment is zero in all these three forms during that symmetric stretching, that is mean position, compressed position and stretched position. In all these positions, dipole moment is zero. Therefore, this symmetric stretching mode is IR inactive. And if you consider another modes, vibrational modes of carbon dioxide, then that mode shows change in dipole moment during the vibration motion. That is, if we consider asymmetric stretching for mean position, that dipole moment is zero, but in another two positions, that dipole moment is positive. Therefore, that shows asymmetric mode and that bending mode also, if you consider, then all the three are that shows change in dipole moment, positive change in dipole moment, therefore that are IR active. Therefore, remember that out of four mode of vibrations, one is IR inactive and another three are IR active for carbon dioxide. Then consider water molecule. Consider water molecule. See here, water is non-linear molecule and therefore in case of water molecule, number of mode of vibrations 3n minus 6. Therefore 9 minus 6, 3 mode of vibrations that are shown here in figure, that symmetric stretching, asymmetric stretching and bending, one only bending. Then that is in plane bending and out of plane bending is the same in case of water molecule. Therefore, if we consider dipole moment, and on the basis of that dipole moment, that all that three modes are IR active, because that shows change in dipole moment. This is condition for um, that IR spectroscopy. Then isotopic effect for this IR spectroscopy, isotopic shift. We already know what is isotopic shift. That is the change in isotopic shift is nothing but the change in fundamental frequency of vibration due to change in the mass by the isotopic substitution. By the isotopic substitution. Because of replacement of simple isotope by another simple atom by their isotope, then what is the change in vibrational frequency of that bond? That change in vibrational frequency is nothing but isotopic shift. Remember this definition. The change in fundamental frequency of vibration. The change in fundamental frequency of vibration. Due to the change in the mass, due to the change in mass by the isotopic substitution. This is known as isotopic shift. Then we know that vibrational fundamental frequency and that atomic masses are related by the equation that phi 0 is equal to 1 upon 2 pi under root k upon mu. That mu is reduced mass, which depends on that atomic masses. And if we consider that k and that pi two terms are constant, therefore this equation become phi 0, that is fundamental vibrational frequency is inversely proportional to under root that reduced mass. Therefore, because of this inversely relation, we can write that phi 0a upon phi 0b. Phi 0a is simple atom and B is their isotope or simple molecule. A is simple molecule and B is molecule where that simple atom is replaced by their isotope. For example, if A is considered as a carbon monoxide having carbon 12 and oxygen 16, while B carbon monoxide having carbon considered 14 and oxygen 16, same. Then phi 0a upon phi 0b is equal to under root mu b upon mu a. Mu b upon mu a. Remember that relation is inversely, therefore that equation. By that, if we consider that phi 0 vibrational frequency in wave number form, therefore phi 0 bar a upon phi 0 bar b is equal to under root mu b upon mu a. Remember this relation for isotopic shift problems. This one is already explained during that vibrational spectroscopy. Then same equation is there. Then Raman spectroscopy. We discuss this Raman spectroscopy next lecture. Thank you.